If you've ever spent, say, 20 hours printing a totally flawless mechanical part, only to watch it warp, sag, or literally shatter the second you actually put it to use, yeah, you know exactly the high stakes we're dealing with today. Choosing the right 3D filament is, without a doubt, the single most critical decision in FDM printing. The success or failure of your printed part doesn't just come down to a perfectly calibrated printer, right? It relies heavily on the actual polymer chemistry of the raw filament you choose to load up. So today, we're going to simplify the science just a bit, making absolutely sure your next batch of printed parts easily survives the real-world environment. Okay, let's dive into this. Here's our quick roadmap for today. First, we'll tackle the heat problem. Second, we'll meet the FDM materials. Third, matching filament to environment. Fourth, avoiding common mistakes. And finally, we'll wrap up with 5 tips for success. I promise you, we are taking this complex polymer chemistry and breaking it down cleanly into highly actionable chunks that you can use right away. All right, Section 1, the heat problem, or why polymer temperature actually matters. So we are essentially setting up the ultimate villain of 3D printing here: environmental stress, and more specifically, heat. Why do perfect 3D prints fail in the real world? It's so incredibly frustrating, isn't it? You spend hours calibrating, you dial in the absolute perfect slice settings. But honestly, none of that matters if you print a functional automotive enclosure or an outdoor bracket out of an organic material like PLA, and then, park your car in the hot summer sun. Your perfectly sliced, incredibly detailed print is just going to soften, sag, and deform right before your eyes under its own weight. And that brings us to a concept you absolutely must know: glass transition temperature. We usually just abbreviate it as TG. Basically, this is the precise temperature threshold where a polymer softens, sags, and loses its structural integrity. Now, it doesn't mean the plastic is melting into a liquid puddle, but it does mean it totally loses its rigidity. Ignoring this essential thermal metric practically guarantees premature part failure. Seriously, if you don't match the TG of your filament to the peak temperatures of your part's operating environment, you are quite literally engineering a part designed to fail. Moving on to Section 2, meet the FDM materials. Let's look at the Big Four. So how do we actually fight back against all that heat and stress? Well, it's time to introduce the 4 main industrial materials we use to combat these physical and thermal challenges on the print farm. This totally brilliantly illustrates the overall landscape, giving us a side-by-side comparison of our Big Four: PLA, PETG, ABS, and ASA. Notice the progression here across print temperature, tensile strength, glass transition, and UV resistance. We start down with PLA, which prints at a super accessible 190 to 220 degrees Celsius with no enclosure needed, all the way up to ABS and ASA. Those demand up to 265 degrees, highly heated beds, and, honestly, mandatory enclosures. The main takeaway? As we step up in thermal endurance, we also step up in printing difficulty. Let's break these down, starting with PLA. Known as the aesthetic king, it's a thermoplastic polyester derived from renewable resources, like cornstarch. Because it has very low thermal contraction, meaning it practically never warps, it is so incredibly easy to print. And surprisingly, it actually has very high static tensile strength. But here is the catch. PLA is highly amorphous and really lacks flexibility, which makes it extremely brittle. Give it a sharp impact and it's going to shatter right along those layer lines. Plus, remember our glass transition temperature? PLA's is a super low 55 to 60 degrees Celsius. Oh, and it degrades pretty quickly outdoors under UV radiation. So definitely the absolute go-to for complex visual details, prototypes, board game pieces, but keep it inside and keep it away from heat. Next up, we have PETG, the tough all-rounder. This is essentially a glyco-modified version of the exact plastic used to manufacture your everyday water bottles. It's widely considered the perfect bridge material between aesthetic PLA and hardcore industrial plastics. Why? Well, unlike PLA, PETG has a really high elongation at break. It bends a bit and absorbs impact energy instead of just shattering into pieces. It also features excellent chemical resistance against things like acids, bases, and alcohols. Crucially, though, it bumps our TG up to a much safer 75 to 80 degrees Celsius. All that makes it perfect for functional indoor components. Think mechanical gears, camera brackets, and chemical containers. All right, Section 3, matching filament to environment. We're talking ABS versus ASA. Now we're moving past those accessible materials and getting into the really advanced high-temperature industrial polymers. Because at the end of the day, your operational environment entirely dictates which one of these you absolutely must use. Now, what's really fascinating here is the precise chemical difference between ABS and ASA. Both of these are absolute powerhouses. They both boast a massive glass transition temperature of 100 to 105 degrees Celsius. So, yeah, they can survive harsh mechanical friction and literal boiling temperatures without losing their shape. Plus, both can be chemically smoothed using acetone vapor for this gorgeous, glossy, watertight finish. But let's look at the critical difference: UV resistance. See, ABS uses butadiene in its chemical backbone, and that breaks down rapidly when bombarded by UV rays. ASA, on the other hand, swaps that butadiene out for an acrylic ester. This one simple change gives ASA the exact same industrial strength as ABS, but makes it completely UV stable. It's a game changer. That brings us to Section 4, avoiding common printing mistakes. Let's talk about the outdoor trap. Because, understanding the raw material data is really only half the battle. A common mistake I see clients make is requesting ABS for outdoor brackets simply because they associate the name with strength. In reality, ABS degrades rapidly under sunlight, turning brittle in a matter of months. This is exactly the trap we just highlighted. Look, ABS is the industrial veteran. It's literally what injection molded Lego bricks are made of. But if you put an ABS part outside, it yellows and degrades fast. So for any outdoor mechanical part, a drone frame, maybe a weather station box, you absolutely must utilize ASA instead, because it will maintain its structural integrity and color for years under harsh sunlight. And finally, Section 5, 5 tips for success. Let's get into some actionable, advanced techniques. The crucial point here is that we need to take all this material science and synthesize it into a practical framework. So here is your field-tested checklist designed to save you time, save you wasted filament, and definitely save you a lot of frustration. Number 1, match TG to the environment. Again, if the part is going in a hot car, keep the PLA far, far away. Number 2, control extrusion viscosity with temperature. Basically, printing hotter lowers the material's viscosity, allowing those polymer chains to interpenetrate for a much stronger layer fusion. Number 3, dry those hygroscopic filaments. Number 4, use enclosures for shrinkage. And number 5, chemically smooth your ABS and ASA with acetone vapor to completely erase layer lines and get that airtight injection molded finish. Building right on tip number 4, let's look at this single number, 1.8%. That is the notoriously high shrinkage rate of ABS plastic as it cools. Now, when a material shrinks by almost 2%, just exposing it to a cool room draft while printing causes it to contract incredibly rapidly. The printed parts will literally curl, lift straight off the print bed, and just split wide open right along the layer lines. This perfectly illustrates exactly why tip number 4 mandates a draft-free, heated enclosure for high-temperature materials. You absolutely have to keep that ambient temperature high to prevent thermal stress cracking. Finally, let's drill down real quick on tip number 3. PETG, ABS, and ASA are all hygroscopic, which means they eagerly absorb water molecules straight from the ambient air in your room. If you don't dry them before printing, that trapped water actually boils inside your printer's hot nozzle. No joke, this creates tiny explosive steam bubbles that completely destroy your part's internal layer structure. You absolutely need to manage moisture in a filament dryer before attempting critical prints. Specifically, you're looking at 65 degrees Celsius for PETG and 75 degrees for ABS and ASA. Doing this prevents those hidden steam voids and guarantees nice, strong, clean extrusion. Well, we have covered the thermal limits, the chemical structures, and the advanced handling techniques required for truly successful FDM printing. So I want to leave you with this final, somewhat provocative thought. What spool is currently loaded on your 3D printer right now? And is it chemically engineered to actually survive your next project? It's far too easy to just default to whatever spool is already hanging on the back of your machine. But as we've explored today, if you want your parts to really last, you have to stop defaulting. Start intentionally engineering your material choices based on the exact physical and thermal environment they're going to face out in the real world. Thank you so much for joining me for this explainer. Now go match your filaments, manage your heat, and happy printing.